Hi there. This video is for section 2.1. In this video, I'm going to be talking about how to find the average rate of change and the instantaneous rate of change and the concepts behind those two things. So let's get started with some examples. We're going to be finding the average rate of change, and I need to first explain what that is. So the average rate of change is how y changes, how the output changes per x. So this thing right here is how y changes per x. And to find out how much y changes per x, we divide by the x change. Now, if this looks familiar, y change over x change, this is commonly written with this delta symbol. That's how y changes per x, or divided by the x change. And that indeed is the formula for slope. And some people have a different version of a slope formula with something like y2 minus y1, x2 minus x1. But the average rate of change is the same formula as the slope. There is a small technical difference in the interpretation, but the calculation is identical. I'll talk about what the instantaneous rate of change is soon. So let's start with calculating the average rate of change. I have some data here on this little grid. I'll zoom in a little bit, maybe to make it easier to see. So we have some points 3, 10, 5, 20, and 10, 50. And I've also tried to put a little context into this. I said let x be the number of seconds since a car left its starting point, and y be the number of feet the car is from that starting point. So the x is going to be the horizontal axis. So this is in seconds. And the vertical is going to be in feet. So just real quickly, if we were to interpret 3, 10, that means after 3 seconds, or 3 seconds after the car has left the starting point, then it is 10 feet from the starting point. So that's how we interpret those kinds of numbers, the x and the y. Okay, so let's go ahead and do part A, this example here, where it says find and interpret the slope between x equals 3 and x equals 5. Well, if you remember our slope formula, that's just going to be the delta y over delta x. We need x equals 3 and x equals 5. Here's the x equals 3 point. Here's the x equals 5 point. You can also read off the y values. So I'll write out the details here. I'll subtract the y values, y2 minus y1. So the second y value minus the first y value. And then I'm going to divide this by the subtraction of the two x values. Just make sure you're consistent with which one is x1 and which one is y1. All right, so 20 minus 10 over 5 minus 3 gives us an answer of 5. So the slope is 5. We also are going to interpret that. So to interpret that, let me remind you that this 20 here, this 20 that we put in here, is not just an abstract 20. It's a 20 from this grid. And the 20 is the y value, which we said before is feet. So this is really 20 feet minus 10 feet. And if you take 20 feet minus 10 feet, the answer here is 10 feet, not just a random 10. And likewise, the bottom numbers are the x numbers, and those are in seconds. So this is 5 seconds minus 3 seconds is 2 seconds. So we have 10 over 2, which is equal to 5. And the words don't go anywhere. We have feet over seconds, which in English is read feet per second. And if you want, we can write this as like 5 over 1 instead of just 5. So it's 5 feet per 1 second. We don't usually write it as 5 over 1, so I'll leave it off for now. But if it helps, write it as 5 over 1 so you can remind yourself that it's 5 feet per 1 second. Remember, you feel free to stop these videos anytime and try these problems yourself. You could try example B at this point. It's always better to be actively learning than passively learning. All right, well, if you had a chance to do B, I'm going to write out my solution for it. Example B says find and interpret the slope between 10 and 5. This is a very similar calculation as we did before, except instead of the 3 and 3, 10, 5, 20, we're going to use x equals 5 and x equals 10 and do our same calculation. delta y over delta x. We need to find how much y changes. Y went from 20 up to 50. So y changed by 30. And x went from 5 to 10, right? It went from 5 to 10, 5 seconds to 10 seconds. So the change in x is 5. And this is feet, and this is seconds. And so 30 divided by 5 is 6 feet per second. All right, so we have the slope between the first 2 points being 5 and the slope between the second 2 points being 6. All right, so first of all, let's reflect on that just for a moment. When you first looked at this problem, it's quite possible, I give this a little context here. There we go. When we first looked at this problem, it's quite possible that you, amongst most other people, saw these dots forming a straight line. In fact, I can draw a little straight line, right here. I have a freehand, but it's pretty obvious that it's straight. But actually, we know it's not straight. A straight line, a line by definition, has to have a constant slope. And we just showed that the slope in this first portion was 5, and the slope in the second portion was 6. And that is not a constant slope. So although this looks like it could be linear, it's definitely not. So we need to be a little careful with using graphs to make conclusions. We need to use graphs to help us, but calculations are really going to be important for us to give definitive evidence whether something is linear or not. All right, so it's not linear. Okay, fine. What are we going to do about trying to interpret the slope at 5? Right now, I'm in example C. All right, so example C. What do we do about interpreting the slope at a particular point? Now, the first thing you should sort of think about is that this is not a sensible question. Slope is how y is changing per how x is changing. It's the y change over the x change. I have to give you 2 points to find how x is changing and how y is changing. You can't really find a slope at a particular point because by definition, slope is how things are changing. So what are we going to do about that? Well, I don't know. I mean, you can imagine we could approximate how the slope is changing at 5 by choosing some points that are close to 5, right? And saying, well, I don't know what it is, but a little bit maybe change to the right, maybe a little bit change to the left. We can try to approximate or estimate the slope at a particular point. This is going to be the instantaneous rate of change, and we're going to make more sense of this in today's video, as well as this is one of the key components of our semester of calculus, is to try to understand what this instantaneous rate of change is, how to make sense of it, how to calculate it, things like that. All right, so we know from the left-hand side, the slope was equal to 5. And we know from the right-hand side, the slope was equal to 6. And we'd like to say that the slope is probably somewhere around 5 or 6. So one of the things we can do just to estimate the slope at a particular point is look at the left, look at the right, and maybe average them together, right? So maybe we could say the slope is approximately 5 plus 6 over 2, the average of those two slopes, which is 11 over 2, or about 5.5. And once again, the units are feet per second because the y changes on the top and the x changes on the bottom. Well, that doesn't seem like a great estimate. And we know this is not linear. And because it's not linear, we don't really know how these points are joined. I mean, I joined them with sort of straight line segments, but they could be joined, with a much more complicated curve. And so, maybe looking to the left and looking to the right, we would get very different numbers than 5 and 6. I mean, presumably we'd have to look much closer to 5 than 3, right? 3 is possibly too far away to get a good estimate. And 10 is even worse, right? So ideally, to get a good estimate at the instantaneous rate of change, we would need numbers close to our target. In this case, close to 5. Something much, much closer than 3 or 10. Now, we don't have that information in this problem. This problem gave very limited information. And so we don't really have the option of getting a better estimate. This is the best we can do. You'll see in today's video how we can get some better estimates and maybe come to some conclusion about what that instantaneous rate may be. All right, let's talk about that subtlety about the slope versus the average rate of change. Slope refers to a constant rate of change. And we know that in this particular graph, there's not a constant rate of change. I don't know if the squiggly line is correct or not, but I do know that there's no constant rate of change between these points. And it may not even be between 5 and or 3 and 5, right? We could have some squiggly line here. So all we can say is on average, the y increases by 5 feet per second. We don't know it's a constant 5 feet per second. So the subtle difference between slope and average rate of change is that slope, is considered the constant value, whereas the average rate of change is that's on average what we increased over that span of time. The instantaneous rate of change is at that moment in time, what is the change in y? I mean, that's essentially what happens when you look at the speedometer in your car. If you look at the speedometer and it says 60 miles per hour, that's at that instant you were looking at the speedometer. It doesn't like say, well, wait 1 second and then I'll tell you the actual speed. It's showing you in real time what that speed is. And what it's essentially doing is it's taking some number of seconds very close to the moment of time, maybe minus 0.1 seconds. And it's averaging the miles in that 0.1 second of change to try to estimate the instantaneous rate of change. So your car actually may be lying just a little bit because it doesn't really know instantaneous rate of change. It can only estimate the instantaneous rate of change, but it does it very accurately because it's collecting data and it can very easily do those calculations. All right, so that's the big setup of what average rate of change is and instantaneous rate of change. Let's do some calculations with some more formulas so we can get a better idea of how to figure out these average rate of change and, more importantly, the instantaneous rate of change. All right, so I have example D here. So in example D, it says to estimate the slope at x equals 5 if we know the equation y equals 1/7 x squared plus 27x minus 20. So let's suppose that this is the equation that matches these dots, right? So you can verify one. You can put in 3 in for x and see if you really do get 10 for y. So that might be a nice little exercise to verify that this equation actually matches all the data points. Regardless, we're going to use the equation to generate additional data because I can put any x value in here and get the corresponding y value. So I don't have to rely on just 3 and 5 and 10 as x values. I can choose any of x values I want. All right, well, to do so, I'm going to use a calculator because I don't want to do all the math myself. I'm going to use an online calculator. The one I'm going to be using is called Desmos. It's a nice calculator. It's free, so I recommend it for folks who are looking for an online calculator. So, and I've prepared a bunch of stuff here ahead of time. So let me get rid of these things just for the moment. I'll be recreating these momentarily, but we'll pretend like it's a mystery at this moment. Okay, so here's the equation. Y equals 1/7 x squared plus 27x minus 20. And it does look like a straight line, but this is one of the key things about using technology is you can't just let the technology do all the thinking for you. You need to do a little exploration. And we've actually already explored paper and pencil, and we know the slope is not constant. So if I zoom out here, I'm going to actually realize this is actually an x squared graph, a parabola. And you might even notice that from the equation. X squared graphs, if you remember your basic functions, are not straight lines, they're parabolas. By the way, you can also go to this little wrench symbol over here and just set the X and Y values that you like, X min and X max, things like that. So you can actually, design whatever window you want without having to zoom in and all stuff like that. It's up to you. All right. What we really want to know is what's happening at X equals 5. So I'm going to put a 5 here. And that gives me a value of 20. So I'm going to actually make it a little bit easier by putting 520 in there and labeling it right there. That's 5, 20. Right? I can label it with numbers, but that's kind of getting in my way. So I'm just going to label it with a dot. So really what we're concerned is what happens right in here. right here at 5, comma 20. All right. What I really want to know is the slope at 5, comma 20. Well, again, I need to have a change in y, and I'm going to be choosing some numbers that are close to 5, so I can have a change in y and a change in x. So what's an example of something close to 5? Well, how about 4.9? So if I choose 4.9, the calculator will instantly tell me that the y value is this 19.472857 number. So if I want to calculate the slope, the approximate instantaneous rate of change, I would do y2 minus y1, 20 minus 19.472857, and 5 minus 4.9, the x2 minus the x1, which is what I've done down here. So this calculation right here is exactly those numbers, and the approximate instantaneous rate of change is this 5.27143 number. Well, 4.9 is definitely close to 5, but we, of course, can get closer, right? So I can go up here and I can choose something like 4.99. And that would give me another y value, but 4.99 is closer to 5. And so my estimate will be better. So here's the numbers here for 4.99. And you can see 5.2843 is the result. And of course, we can do other numbers. We can do, I'll just do 4 nines this time. So 4 nines, that's 3, there's 4, is this 19.99 number. That's this one right here. And it ends up being 5.29. And I can keep doing more nines if I so choose, and continue doing the slope calculation. And you actually get something very, very close to 5.3. Right. At some point, these online calculators, well, all calculators, in fact, will have to start rounding things because they can't show you an infinite number of zeros. So at some point, they're going to start rounding. This calculation, if you think about it, is not exactly equal to 5.3. It's, 5 point, very close to 5.3, right? So it's rounding at some point, but we can really get an idea that as we get closer and closer to 5, 4.9, 4.99, 4.999, the slope value, the instantaneous rate of change estimate, is getting closer and closer to 5.3. So that's how we're going to estimate it using, a graph or a table in this case. Now, please be aware, we need to be mindful of the slope on the left and the slope on the right. There's no reason why we should just think about numbers that are very close to 5 and less than 5. We should also consider numbers which are close to 5 but larger than 5. For example, 5.1. 5.1 gives me a y value that's a little bit bigger than 20, and I can do my slope calculation. 20 minus, that's the y value for 5 minus 5.001. Oh, I can change this to 5.1, and I get, okay. Sorry about that. I'm not going to do a lot of these because I guess I decided when I was going through my practice run that it's just too much time to write down all the 5.1, 5.01. So I kind of jumped to 5.001, which I'm not advising you do. But I just want to have some, sort of efficiency with these videos. So there's the 5.001, and when I do the calculation, I get 5.29, and we could do more numbers here to be able to find better and better estimates. But you can see that perhaps when you take numbers larger than 5, like 5.001, we still get a slope, an instantaneous rate of change of close to 5.3. Now, we'd like to say that it's 5.3, and I think that's a good estimate. We don't know for sure it's 5.3. We have very good evidence that it's 5.3, but we need to do a little bit more math. We're going to develop a little bit more, tools to actually figure out exactly what that instantaneous rate of change without having, this sort of a little bit of guesswork. And please be aware when you're doing these problems, do write out a table. Like some people just say, oh, I'll just do 4.9999 and get an answer and be done with it, right? Or they'll do one bigger number and one smaller number and be done with it. Just be aware that you need to see a pattern. You need to see numbers that are getting closer and closer and closer to a number, because I can trick you. I know enough math where if you just do 4.999 and 5.001, I can make it actually an answer different than what you might see with just a couple of numbers, one number, two numbers. So try to use several numbers, even though I promise I won't trick you too much. But just be aware that this method requires a sequence of numbers that get closer and closer, approach a particular value. All right, so what I did next was I graphed the line with the slope, the instantaneous rate of change of 5.3. And the way I graphed it was the y minus y1 equals mx minus x1 equation. I took this 20 over here. This was actually y minus 20 over here. So y minus y1 equals the slope, 5.3, times x minus x1. But as I mentioned before, it's considered good manners to have y by itself. So we're going to move the minus 20 to the right by adding 20. So that's the equation right there. And I'm going to visualize it by clicking on this. So there's the line right there. So the line goes straight, obviously, because it's a line, and it seems to overlap the parabola close to 5. In fact, if I zoom in close to 5, it's kind of hard to see that there's two things there. I mean, we know there's two things there, but right here, we're on a very small scale. The x values are very close to 5. Let's see what they are. Like, 4.9, 4.99, 5.01. So we're really close to 5. The line looks kind of identical, at least in terms of the values, as the parabola. So this is the tangent line. It's the line that goes in the exact same direction as the curve, as the parabola in this case. The difference between the two is marginal, if not, insignificant. And so we're going to be using this tangent line to help us understand the function. And this is the big idea behind calculus. Any complicated function can be broken down into little pieces where each little piece looks like a line. If we understand all those little pieces really well, if we understand those lines really well, then we can put it back together and understand the entire function. Now, that whole deconstruction and reconstruction process is what we're doing this semester in calculus. So I can't explain it at this moment in chapter 2, but it is the idea behind our calculus. All right, so that's the line right there. And I just wanted to show you how it approximates, or really, is essentially the same thing as the curve right near our objective point, which is 5. Okay, so let's go back to my lecture notes here. So we estimated the slope at x equals 5 by using a sequence of x values getting closer and closer and closer to 5. We looked at numbers smaller than 5 and larger than 5, and we got a slope approximately 5.3. And that is supposed to be 5.3 feet per second, right? We know that this is the change in y over the change in x. And so we want you to be thinking contextually for a lot of these problems, not just it's an abstract calculation, but it's measuring, in this case, the instantaneous velocity in feet per second, 5.3 feet per second. It's also important to note that we don't just have to work on time and distance. Those are, nice variables to talk about, but we could change this problem contextually by saying, let's let x be number of hours and let's y be number of dollars. So when we're doing our calculation, we're still doing the exact same numbers. We're still getting a slope of 5.3. But what are the units now? Well, the units are change in y over change in x. The y is number of dollars earned. So this is dollars, or if you want to say dollars earned, that's fine too, per number of hours, per hour. So on average, or I guess at that instant in time, at x equals 5 hours, we're earning at a rate of $5 per hour. Anyway, so we can use whatever words, whatever units we want, and calculate these rates, these instantaneous rates, or at least estimate the instantaneous rates. All right, let's look at another problem. I have a new function, 5 equals 3 times 2 to the x, and we're trying to estimate the slope at x equals 4. Just a friendly reminder to pause the video and try these problems if you feel comfortable doing so. If you just want to watch, that's okay too, but I'll just keep reminding folks that that is a good strategy if you're willing to do it. Okay, well, I'm going to apply the same technique as I had before, I have a function. It looks like this. I have a point 4, 4 comma 48, if you can see that. And I'm going to use my graphing calculator to estimate the slope at x equals 4. Estimate the instantaneous range at x, its instantaneous rate of change at x equals 4. All right, so let me turn off this line here and this other curve. And let me turn on this new graph. So there's the f(x) graph. I'm going to hit the home button to make it return back to its normal, grid. Oh, there we go. There's the graph. And maybe I'll adjust it a little bit, like over here. Now I want to know what happens at x equals 4, right? I know that because the directions tell me I want to find out what happens at x equals 4. X equals 4 right here, right? It even tells me on the little grid here, it's 4 comma 48. So let's see what that's going to be. So I can put a 4 in here. And yep, there's 48. I used f of x instead of y because it's a nice way of getting the calculator to build more complicated functions. I'll show you that in a second. So just like before, we'd like to choose a number close to x, like 3.9 or 3.99, something like that. And we can find the change in y over the change in x. Now, instead of me typing all of this in every single time, I just made a new function. G of x is the y value, 48, minus the f of x value, the y value from the f function. So if I put in a value of 3.99 into this thing, it'll do 48 minus the y value at 3.99 divided by 4 minus that 3.99 number. So I've created a function here, g of x, which calculates the slope, y2 minus y1, x2 minus x1, assuming this is, my x2, y2 up here. Doesn't matter the order. So I'm going to put in here an x value, 3.99, and it's going to do the y2 minus y1 over x2 minus x1 for me. So this is calculating the slope. So the slope is about 33.15. So this is much faster than me typing out the calculations themselves. And of course, I can do a sequence of values very quickly, getting closer and closer and closer to 4. And I can look on the other side as well. I can have numbers that are bigger than 1 or bigger than 4, and it will calculate the slope there. There we go. All right. So at some point, if I get too close to 4, it'll just round it. It just ends up doing rounding off the numbers because it's too it's too close to 4 for it to be able to do all the numbers. So I'm not sure what it is here, but eventually you'll see that with enough numbers, it'll start rounding it to a number, and you won't be sure about the accuracy of your slope. But we're only estimating. So what do we got here? 33.1, 33.2, 33.2. It looks like it's getting closer to 33.26. Maybe it's getting closer to 33.5 or 34. What about bigger numbers? For 4.01, it's 33.3. Closer to 4 is 33.2. Even closer to 4, a ton of zeros, is 33.27. So it looks like it's close to like 33.27 or something like that. Again, it's not exactly clear what the exact number is just by using data to approximate that. So that's why we need the calculus formulas so we can find these instantaneous rate of change more precisely. But we certainly know it's right around, let's say 33.3, something like that. All right, so for doing a homework assignment, you would show the table you're using, or copy and do a little screenshot of the little table. You would show the table, you would show the slope values, and you would say the slope is approximately, I forgot the number, 5.3. I'll go check in a sec. Okay, I was off. 33.3. Okay, sorry about that. Oh, with 5.3 is the last problem. Yeah, okay. Yeah, okay. All right, so let me erase this 5.3 and let me change it to 33.3. Now I don't have words for this one, so you don't have to worry about the units. I didn't say feet or seconds or anything like that, but 33.3 is an approximate instantaneous rate of change. Now, with some calculus that you're going to be learning starting in chapter 3, we're going to figure out that the slope is actually equal to 3 times 2 to the fourth power times the natural log of 2. And you're wondering, where does that come from? Like, how did you know this? Again, this is from chapter 3, and we are in chapter 2, my friends. So I'm not going to do chapter 3 material right now, but we can calculate these things very precisely using our formulas. Okay, so that's a little foreshadowing for the future. The slope at a point thing is called the instantaneous rate of change, as I mentioned before. All right, and we have this last example. We have a function g of x equals x squared plus x minus 1, and we want to estimate the instantaneous rate of change at x equals 2. Surprisingly, or maybe not so much so, we're going to be using the same kind of calculations as we did before. Since we don't have all our chapter 3 formulas, we have x squared plus x minus 1. We can do y2 minus y1 over x2 minus x1, and we can calculate those different slopes. Right, so I can do a table here for the ix function. Let me do a table here. Table. There we go, table. And we have different values of x. We can't plug in 2 directly because there would be no change in x. We're starting at 2, so we need something slightly bigger than or slightly smaller than 2. So I can choose like 2.001, 2.00001, etc. Right? And I can get numbers that hopefully form a pattern, and then I can see what's going on here. So maybe you can see the pattern already with the numbers that are slightly bigger than 2. Let's use a few numbers that are smaller than 2. Smaller than 2 would be 1.9, not 4.9. There we go. And then 1.999. And for most folks, they're starting to see a pattern already. It's getting closer and closer and closer to 5, both from bigger numbers from the right side and from smaller numbers on the left side. So we would conclude that apparently the instantaneous rate of change is somewhere right around 5. So these are some examples of how to find the instantaneous rate of change. And once again, when you're showing your work like on a lab assignment or a test or something, you would have to provide the evidence. You'd have to show the table of values. You'd be showing the x value 2 and 2.001 or 2.001 or maybe 1.99. You'd want to show those numbers, and you could just take a screen grab to make things easier for that calculation. Right? You also have to calculate the slopes, by the way. Again, feel free to use technology to help you with these calculations. Okay, and just some vocabulary to end today's video. If you have 2 points, like when x equals 2 and x equals 2.001, those are 2 different points, and you find the slope between those 2 points, that's called a secant line. Secant line is the slope through 2 points. And when we talk about the slope at a point, that is what we call a tangent line. This is a slope at, and I'll still put quotation marks there, at a point, right? At 1 point. I'll just say 1 just to make it consistent with the previous number. So how we find the slope at a point and how do we interpret that, etc. That's what we're going to be doing. The slope at a point is called the derivative. So if you've heard the word derivative before, because it's imperative or it's a big part of calculus and you know it's about derivatives, that's the slope of the tangent line at a point, right? Slope of the line tangent to the graph at that single point. That is called the derivative, and we'll be studying derivatives in every single chapter, starting in chapter 2. Okay, so that's the end of today's video. Hopefully you found it useful, helpful. Please reach out if you have any questions, and I hope you have an enjoyable day.